Hey everyone, and welcome back for another deep dive.
Always happy to be back.
Today we're going to be tackling something that's both incredibly powerful and strangely weak.
Yeah, it's a bit of a paradox.
We're talking about gravity.
The force that shapes galaxies and makes apples fall from trees.
But also the weakest of the four fundamental forces.
By far the weakest.
So how can something be both so mighty and so meek? You know, us humans, we've always been fascinated by the biggest and most powerful things.
Oh yeah, for sure.
Take the Tsar Bomba, for example. The largest nuclear weapon ever detonated.
Oh yeah, I remember reading about that.
It was back in 1961. The Soviets dropped this 27-ton behemoth over an island in the Arctic Ocean.
Really? 27 tons?
27 tons.
Yeah, wow.
The explosion was 50 megatons of TNT.
That's
over 3,800 times the power of the bomb dropped on Hiroshima.
unbelievable.
Just the visuals alone are insane. A mushroom cloud towering 60 kilometers high, a flash visible 1,000 kilometers away, and heat so intense it could cause third-degree burns from 100 kilometers away.
100 kilometers away. That's terrifying.
It's crazy, right?
Yeah.
But here's the thing. As terrifyingly powerful as the Tsar Bomba was, it's nothing compared to the events that routinely occur in space.
Right.
Supernovae, for example, are the explosive deaths of giant stars, and they release energy that makes our most powerful weapons look like, well, firecrackers.
Yeah, it's hard to even fathom that kind of energy.
And then you've got hypernovae, which come from the collapse of even larger stars, and they make supernovae look tame in comparison.
Yeah, it's hard to wrap your head around.
So what force drives these cosmic powerhouses?
Gravity, of course.
Gravity, of course, but here's where it gets weird.
Okay.
Gravity is actually the weakest of the four fundamental forces in the universe.
You got it.
So you've got the strong nuclear force holding atoms together.
Right.
You've got electromagnetism governing light and energy.
Uh-huh.
The weak nuclear force behind radioactive decay.
Yep.
And then you've got gravity bringing up the rear.
It's kind of the runt of the litter.
It really is. It's a bit of a head scratcher, isn't it?
Yeah, for sure.
We experience gravity constantly.
Mm-hmm.
It shapes the universe on a grand scale.
Right.
Yet it's incredibly weak compared to the others.
Absolutely.
It's like this invisible hand that's both omnipresent and barely noticeable.
It is a paradox, isn't it? And that discrepancy, the fact that gravity is so much weaker than the other forces,
Yeah.
that's what we physicists call the hierarchy problem.
The hierarchy problem.
Yeah, it's one of the biggest mysteries we're grappling with.
Okay, so we have this force that's both mighty and meek.
Right.
It's responsible for the most powerful events in the universe, yet an ant can defy it.
That's a great way to put it.
How do we even begin to wrap our heads around that?
Well, the story of our understanding of gravity is full of twists and turns.
Oh, I bet.
And it all starts, like many scientific breakthroughs, with a simple observation.
Ah, you mean Newton and his apple.
Exactly.
The year is 1666. The plague is raging, and Newton's chilling at home because Cambridge University is closed.
Having to work from home.
Right. As the story goes, he's sitting in his garden when thunk, an apple falls from a tree.
You know what they say? Sometimes the simplest things spark the biggest ideas.
And did it bonk him on the head? I mean, who knows?
I've always wondered that myself.
Yeah, right.
But
the important thing is that this everyday event got him thinking.
You got it.
Why do things always fall down? Why not sideways or up?
Exactly.
What is this unseen force pulling everything towards the Earth?
He was really onto something.
And from that simple question, he developed his law of universal gravitation.
It's amazing what a falling apple can do.
I know, right? So every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them.
One of the fundamental laws of physics.
That's pretty revolutionary for the 17th century.
Oh, absolutely. It was a huge leap forward.
It was, right.
It explained why planets orbit the sun in elliptical paths and why we have time.
But here's where it gets interesting. Newton himself wasn't entirely satisfied with his own theory.
Really?
He cracked the code on gravity and he wasn't satisfied?
Well, you see,
What was missing?
his theory could calculate the force of gravity, but not how it worked.
Okay.
How can objects separated by vast distances pull on each other without anything connecting them?
Yeah, that's a good question.
This action at a distance, as he called it, seemed absurd to him.
I can see why he would think that.
He even said, and I quote, that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has, in philosophical matters, a competent faculty of thinking can ever fall into it.
So even the father of gravity knew there was more to the story.
Exactly.
It's like he built the foundation, but knew a whole structure was missing on top.
A perfect analogy.
And that sense of something missing
Right.
set the stage for a truly revolutionary idea.
And what's that?
Curved space-time.
Now we're talking.
Okay, curved space-time, now we're talking. But how did we get from falling apples to warping the fabric of reality?
Well, we need to fast forward to the early 20th century
Okay.
and meet a Finnish physicist named Gunnar Nordström.
Gunnar Nordström?
He was inspired by Einstein's theory of special relativity, which proposed that the laws of physics are the same for all observers moving at a constant speed.
Okay.
And that the speed of light is constant, leading to some wild effects like time slowing down and distances shrinking as you approach the speed of light.
Right. Special relativity. I remember learning about that.
It's mind-bending stuff.
It's mind-bending, but it's been proven again and again.
Oh, absolutely.
So how did Nordström build on that?
He took Einstein's idea of space-time, this unified fabric of space and time, and applied it to gravity. He suggested that maybe space-time wasn't flat, but curved, and this curvature caused objects to move towards each other.
So he was saying gravity wasn't a force pulling things together,
Right.
but the result of objects following the contours of a warped space-time.
That's a great way to put it.
That's a whole different way of looking at it.
Absolutely a truly groundbreaking idea.
It is groundbreaking.
However,
There's a however.
there's always a however.
Right.
His math couldn't quite explain certain observations like how light bends around massive objects.
So close, but no cigar.
Yeah, you could say that.
But his ideas must have been a stepping stone for someone else, right?
You guessed it. Nordström laid the groundwork for Einstein to develop his theory of general relativity, which did incorporate curved spacetime and really revolutionized our understanding of gravity.
This is where things get really complex, right?
It can be a bit mind-boggling.
General relativity is notoriously difficult to wrap your head around.
It is. But Einstein was great at explaining complex ideas with simple thought experiments.
Thought experiments, I love those.
Me too.
One of the most famous involves a man falling from a building.
Oh, yeah. The falling man.
Okay, I think I've heard so. Hope he's got good insurance.
Well, hopefully it's just a thought experiment. So imagine a man falling from a very tall building. As he falls, he releases an object he was holding.
Okay.
From his perspective, the object floats right next to him, as if there's no gravity.
So from his point of view, he's weightless, even though he's plummeting towards the ground.
Exactly.
It's wild.
It's all relative.
I see.
And this illustrates the equivalence principle.
Okay.
The effects of gravity are indistinguishable from the effects of acceleration.
Okay, I'm following so far.
Yeah.
But how does this tie into the whole curved space-time idea?
Let's tweak the thought experiment.
Okay.
Now, the man is inside a box, floating in space, truly weightless. But then the box starts accelerating upwards at a constant rate.
Okay.
What happens to him?
Well, if the box is accelerating upwards, he's going to feel pressed against the floor.
Right.
Just like he would if he were standing on Earth.
Exactly.
But wouldn't he be able to tell the difference between that and actual gravity?
That's the point. He experiences the same sensation of weight even though there's no gravitational field.
I see what you're saying.
The acceleration mimics the effect of gravity. And this is where the curvature of space-time comes in.
Okay.
Einstein realized that gravity isn't a force in the traditional sense,
Okay.
but a manifestation of this curvature.
Got it.
Massive objects like the Earth or the Sun warp the fabric of space-time around them, and this warping dictates how other objects move.
So instead of the Earth pulling on us with a gravitational force, it's more like we're rolling down a hill created by the Earth's mass warping space-time.
That's a great way to visualize it.
Objects follow the straightest possible path through curved space-time. And those paths appear to us as the curved trajectory of gravity.
That's the beauty of Einstein's theory.
Okay, that's pretty mind-bending.
It is mind-bending.
But if it's so complex, how do we know it's actually true?
That's the key question, right?
Did Einstein just make all this up?
Not at all. General relativity has been tested and confirmed in countless ways.
Really? How so?
For example, it accurately predicted the weird wobble in Mercury's orbit.
Oh, yeah. Mercury's orbit was always a bit off.
Right, which Newton's theory couldn't explain.
Okay.
And it perfectly predicted the bending of light around massive objects, which was observed during a solar eclipse back in 1919.
So Einstein's theory not only explained everything Newton's theory could, but it also went further and explained things Newton's theory couldn't.
Exactly.
That's a paradigm shift.
It absolutely was.
And it revolutionized our understanding of gravity and the universe as a whole.
It really did.
However,
Here we go again.
There's a however.
Always a however.
Right.
Even though general relativity describes how gravity works, It doesn't tell us the origin of gravity. Why does mass warp space-time in the first place?
Yeah.
What's the underlying mechanism?
So we've come a long way since Newton's apple.
We have.
But the mystery of gravity's origin remains unsolved.
The quest continues.
What happens next in our story?
Well, that's a story for another time.
Oh, come on.
Gotta save some of the mystery.
All right, fine, but you've got to come back.
I wouldn't miss it.
All right, so stay tuned for part 2 of our deep dive into the mystery of gravity.
It's going to be a wild ride.
It's going to be epic.
Well, that question, the origin of gravity, is what has driven physicists to explore some of the most extreme environments in the universe.
You mean like
Black holes?
black holes?
Neutron stars.
Neutron stars?
And even the echoes of the Big Bang itself.
Exactly.
Hey, now we're talking, that's where modern gravity research comes in, right?
Absolutely.
And I know we can't talk about modern gravity research without mentioning LEGO.
The Laser Interferometer Gravitational Wave Observatory.
LEGO, that's right.
It's been a game changer in our quest to understand gravity. So before LEGO, our understanding of gravity was mostly theoretical, right?
Largely, yeah.
We could see its effects on planets and stars, but we couldn't directly observe gravity itself.
Right, it was all based on...
What did LEGO change?
Well, before LEGO, we were essentially deaf to a whole symphony of cosmic events.
A symphony of cosmic events. I like that.
LEGO was designed to detect gravitational waves, those ripples in space-time that Einstein predicted, caused by some of the most violent events in the universe.
Events we couldn't see with traditional telescopes.
Exactly.
So these are ripples caused by the collision of incredibly massive objects.
You got it.
Like, what kind of collisions are we talking about here?
Picture this about 1 billion years ago. 2 black holes each. More than 30 times the mass of our sun were locked in a gravitational dance.
Okay.
Spiraling closer and closer. Eventually, they collided in a cataclysmic merger.
Wow, talk about a cosmic demolition derby.
I know, right?
But what does that have to do with us here on Earth 1 billion years later?
That collision sent powerful shock waves.
Okay.
Those gravitational waves rippling through space-time. And after traveling for over 1 billion years at the speed of light, these waves finally reached Earth on September 14th, 2015.
Okay.
At precisely 9:50 a.m.
Hold on, you're giving me a very specific date and time.
I am.
Did someone actually see this collision?
Not with their eyes, but with LEGO.
Right, LEGO. So how does it work?
Well, it's pretty ingenious, actually.
Detecting ripples in space-time sounds incredibly difficult.
It is incredibly difficult.
Did they actually manage to build something sensitive enough to do that?
It was a massive undertaking, for sure.
Yeah, I'll bet.
LEGO uses lasers to measure tiny changes in distance caused by passing gravitational waves.
Lasers, okay.
Imagine a ruler so precise that it can detect changes smaller than the width of a proton.
That's insane.
It is pretty mind-blowing.
And this actually worked.
It did.
There was a lot of skepticism around the project, wasn't there? I mean, who could blame them?
In fact, when the researchers first detected the signal, they were so surprised, they thought it must be a mistake.
Really?
A test signal someone had injected into the system.
Wow.
They couldn't believe it was real.
So I can only imagine the feeling when they realized they had actually detected gravitational waves from a black hole merger.
It was a eureka moment for sure.
It was a monumental moment for physics.
It really was.
Since that first detection, LEGO has detected numerous other gravitational waves.
Many more.
Including those from a neutron star merger back in 2017.
That's right.
So we went from not even knowing if gravitational waves were real to detecting them regularly.
It's amazing how quickly our understanding can change.
That must have completely changed our understanding of the universe.
It did in many ways.
So tell me more about that. How did these observations impact our knowledge of gravity?
Well, these detections have not only confirmed Einstein's theory,
right,
but they've also opened up a whole new way of observing the universe. We can now listen to events that were previously invisible to traditional telescopes.
Listen.
Yeah, it's like we were looking at a silent film, and suddenly we have sound.
That's a great analogy.
It really is a whole new sense with which to explore the cosmos.
It makes you wonder what else we're missing. What else is out there that we can't see or hear with our current instruments?
It's a question a lot of physicists are asking.
It is a good question.
And it leads us to the next chapter in this story.
Okay, what's that?
The search for primordial gravitational waves.
Primordial gravitational waves? What are those?
Waves that originated from the Big Bang itself.
Wait, you're saying we can potentially detect ripples from the very beginning of the universe?
We might be able to.
How is that even possible?
Well, our current model of the early universe suggests a period of rapid expansion called inflation.
Okay.
Which happened just fractions of a second after the Big Bang. This inflationary period would have generated gravitational waves. And those waves should still be permeating the universe today, like an echo from the dawn of time.
So it's like trying to hear a whisper from billions of years ago, except the whisper is a ripple in the fabric of reality.
A very faint whisper.
A faint whisper, right? But if we're just starting to detect gravitational waves from black holes and neutron stars, how can we possibly hope to detect something so faint?
That's the challenge, isn't it?
Wouldn't that require instruments far more sensitive than LIGO?
You're absolutely right. While LIGO was groundbreaking, it's not sensitive enough to detect these primordial waves.
So what can we do?
Well, newer, more advanced instruments are in development.
Okay.
Like the European Space Agency's LISA mission.
LISA?
Yeah, it stands for Laser Interferometer Space Antenna.
So LISA is like LIGO's superpowered cousin.
You could say that.
And what could detecting these primordial waves tell us?
Oh, so much.
Would it just confirm our current model of the Big Bang?
It'd be a huge step towards confirming our model, of course.
Or is there something more to it?
But it could also tell us a lot more.
Okay.
Primordial waves could give us a glimpse into the very first moments of the universe,
really?
Revealing details about the end of inflation.
So we could actually learn about the end of inflation?
We could.
Okay.
Was it a slow, gradual process or a sudden, rapid event?
How could these waves tell us that?
The shape and intensity of the waves could hold clues.
Okay, so we're talking about understanding the birth universe.
We are.
That's incredible. But is there anything else we could learn from these waves?
Possibly.
Anything that affects us more directly here and now?
They could help us answer one of the most fundamental questions about gravity itself.
Okay.
Is the gravitational field truly fundamental to the universe?
You know, that's a question I've always wondered about.
It's a big one.
We know mass warps space-time and that creates gravity. But what is it about mass that causes this warping?
That's the million-dollar question.
What's the connection between mass, the Higgs field, which gives particles their mass and gravity? You see, while the Large Hadron Collider discovered the Higgs boson, it's still unclear how this all connects to gravity at a fundamental level.
It's one of the biggest mysteries in physics.
So detecting these primordial waves could potentially reveal the connection between the very fabric of the universe and the particles that make up everything we see and experience.
It's a tantalizing possibility.
It could revolutionize our understanding of reality as we know it.
It really could.
Okay, so we've got these mind-blowing theories about the universe.
Yeah.
Incredibly sensitive instruments like LIGO and LISA. And the potential to unlock the secrets of gravity itself.
It's an exciting time to be a physicist.
But where do we go from here? I mean, are there other approaches to solving this mystery?
There are.
What other avenues are physicists exploring?
You're right. We've come a long way, but the story of gravity is far from over.
Okay, good.
And yes, there are many unanswered questions and some pretty radical alternative theories out there that push the boundaries of what we thought was possible.
This is where things get really interesting, right?
Things are about to get really weird.
Now we're going beyond traditional theories of gravity and stepping into some uncharted territory.
Fasten your seat. You know, a lot of people don't realize that traditional theories of gravity start to break down when we try to apply them to the incredibly small scales.
Oh, you mean like the Planck scale?
Exactly. At those scales, the math just doesn't add up.
So what are physicists doing about that?
Well, they're coming up with some pretty wild ideas.
Like what? Give me an example.
Well, one approach is called loop quantum gravity.
Loop quantum gravity.
Yeah, it's based on the idea that space-time itself is quantized.
Quantized.
Meaning it comes in discrete chunks like pixels on a screen.
So instead of a smooth, continuous fabric,
right,
space-time is made up of tiny building blocks.
Exactly. And these building blocks are woven together in a kind of network or a spin network.
A spin network? That sounds complicated.
It is, but the basic idea is that these networks of interconnected loops give rise to the geometry of space-time.
And that geometry determines how gravity works.
Exactly. It's a pretty radical departure from traditional theories.
It is a radical departure, but is there any experimental evidence to support it?
That's the thing with these really out there theories. It's incredibly difficult to test them experimentally.
I bet.
But physicists are working on it.
They're always pushing the boundaries.
They are.
So loop quantum gravity is one approach. What are some of the other alternative theories out there?
Well, another prominent one is string theory.
String theory. Yeah, I've heard of that one.
It's one of the most mind-bending theories in all of physics.
Okay, so tell me more about it. What's the basic idea behind string?
Well, the basic idea is that the fundamental building blocks of the universe are not particles.
Not particles.
But tiny vibrating strings.
String.
And the different vibrations of these strings give rise to the different particles and forces we...
So everything we see and experience is just the result of these tiny strings vibrating in different ways.
That's the idea.
That's pretty wild.
It is pretty wild. And it gets even wilder.
How so?
String theory also predicts the existence of extra dimensions.
Extra dimensions.
Dimensions beyond the 3 spatial dimensions and 1 time dimension we're familiar with.
Okay, so you're saying there could be more dimensions out there that we just can't perceive?
Exactly. It's kind of like being a flatlander living in a 2-dimensional world. You can't perceive the 3rd dimension, but it's there.
I think I get it. So these extra dimensions are curled up or hidden in some way.
That's right. They're compactified.
Compactified. Okay, I'm trying to keep up here.
But they still have an impact on the physics of our universe.
Okay, so how does string theory explain gravity then?
Well, one way it does this is through the concept of brane.
Brane.
Yeah, branes are these higher dimensional objects that exist in string theory.
Right.
And our universe might be just one 3-dimensional brane floating in a higher dimensional space.
So our entire universe is just like a slice of bread in a cosmic loaf.
That's one way to visualize it.
And gravity could be leaking.
Exactly. Gravity might be much stronger in these higher dimensions.
Which could explain why it seems so weak in our 3-dimensional world.
Precisely. It's like the force of gravity is spread out over more dimensions, so it's diluted in our universe.
Okay, I'm starting to get the picture here, but it's still pretty mind-boggling.
Oh, it definitely is mind-boggling.
All these extra dimensions and vibrating strings and branes.
But it's a fascinating area of research, and it could hold the key to understanding some of the deepest mysteries of the universe.
I agree. It's been an amazing journey exploring these ideas with you.
The pleasure was all mine.
And I think we've given our listeners a lot to think about.
I hope so.
So until next time, keep looking up at the stars and pondering the mysteries of the universe.
And who knows, maybe you'll be the one to unlock the secrets of gravity.
That's right. You might be the next Einstein.